There is a version of you reading these words in a universe almost identical to this one, except that a quantum event that went one way here went the other way there, and the consequence of that difference has propagated through time in a way that made your life slightly different, or very different, or unrecognizably different, or made it so that you never existed at all. There is, in another universe, a version of the solar system that formed without a planet in the habitable zone, and there is no life in that universe of any kind. There is, in another universe, a version of physics in which the electron mass is slightly larger and atoms are unstable, and there are no molecules, no chemistry, no complexity of any kind beyond the simplest nuclear reactions. There is a universe in which the cosmological constant is 1,000 times larger than in ours, and the universe expanded so fast that no galaxies ever formed and the stars never lit. There is a universe in which it is larger still, and the universe expanded so fast that it was cold and empty within fractions of a second of the Big Bang. There are universes, most universes, in the vast ensemble of what is theoretically possible, that are dark and cold and empty and have been so since moments after their origin, that contain no structure and no complexity and no life and will never contain any, that expand forever in silence and darkness and will do so until even the quantum fluctuations that ripple through their vacuum decay away to nothing. And there is this universe, the one you are in, the one with the specific electron mass that allows atoms to exist, the specific cosmological constant that allowed galaxies to form, the specific strong nuclear force that allows carbon to be synthesized in stars and released in supernovae and assembled into biology, the one in which the Higgs field has the specific vacuum expectation value that gives quarks and electrons the specific masses that make chemistry possible, the one in which the ratio of the electromagnetic force to the gravitational force has the specific value that makes stars burn at the right rate for billions of years, long enough for planets to form and cool and for life to develop and for intelligence to emerge and for someone to lie awake at night wondering about all the other universes that are not this one. Whether those other universes are real, whether they physically exist in any sense that the word exist can meaningfully carry, is the question on which some of the greatest scientific minds of the last 50 years have divided into camps, and the debate between those camps is the most important unresolved argument in contemporary physics. It is important not just for what it says about cosmology, about the large-scale structure of reality, but for what it says about science itself, about what it means for a theory to be scientific, about whether a claim about the world counts as knowledge if it cannot, even in principle, be tested, about whether the universe or the multiverse owes us the courtesy of being comprehensible to creatures like us, with our instruments and our mathematics and our limited perspective from one small rock in one of 100 billion galaxies in one of what may be an infinite number of universes. This is the story of the multiverse, not as a concept from fiction, but as a serious and deeply contested idea that emerges from the physics we know, from equations that have been tested and confirmed in every laboratory experiment that has ever been done, from theories that predict with extraordinary precision the mass of the Higgs boson and the anomalous magnetic moment of the electron and the spectrum of the cosmic microwave background. It is the story of how serious physics, following its own internal logic to conclusions that its practitioners did not always want to reach, arrived at the idea that our universe is one among an unimaginably vast number of others. And it is the story of the argument about what that idea means, and whether it deserves to be called science, and what we lose and what we gain if it turns out to be true. To understand the multiverse, you have to understand how many different paths lead to it. Because the multiverse is not a single idea. It is a family of ideas, connected by the theme of our universe being one of many, but arising from completely different theoretical frameworks, each with its own motivation and its own evidence and its own problems. There are at least 4 distinct versions of the multiverse that physicists take seriously, and they are not mutually exclusive. All 4 could be simultaneously true, or none of them, or some combination. The fact that multiple independent lines of reasoning converge on the conclusion that our universe is not alone is the most powerful argument for the multiverse. The fact that each of those lines of reasoning has its own serious problems is the most powerful argument against it. The first and most straightforward version of the multiverse requires no exotic new physics at all. It requires only that the universe is large, genuinely, incomprehensibly large, and that the laws of physics that govern our region of space govern all of it. In an infinite universe, or even a sufficiently large finite universe, every possible arrangement of matter and energy that is consistent with the laws of physics must occur somewhere, simply because there are only finitely many distinguishable arrangements within any finite region of space, and if you tile enough copies of that finite region together, the arrangements must repeat. In a universe large enough, there is another version of you, made of different atoms but in the same arrangement, living what is for all practical purposes the same life. The distance to your nearest cosmic twin in a universe of infinite extent with the same laws of physics and the same initial conditions can be estimated. The answer is around 10 to the power of 10 to the power of 28 meters, a number so large that writing it out would require more digits than there are particles in the observable universe. Your nearest twin is not accessible to observation, but in an infinite universe they exist as surely as you do, as a consequence of combinatorics and the laws of probability. This version of the multiverse, sometimes called the level 1 multiverse, in the taxonomy proposed by the cosmologist Max Tegmark, requires no new physics at all. It is a consequence of the universe being large, which is not in dispute. The observable universe, the region from which light has had time to reach us since the Big Bang, is a sphere about 93 billion light-years in diameter. But the universe almost certainly extends beyond this horizon. How far beyond is unknown. Inflation, the period of exponential expansion in the first fraction of a second after the Big Bang, stretched the early universe to a size enormously larger than the observable horizon, and the specific models of inflation that best fit the CMB data predict that the total universe is at least 10 to the 23rd times larger than the observable universe, and possibly infinite. In a universe of this size, the level 1 multiverse is not a speculation but an inevitability. The objection is not that the level 1 multiverse doesn't follow from the physics. It is that the other regions of the universe, the regions beyond our observable horizon, can never be observed, and therefore their existence, while logically implied by our best theories, is not scientifically accessible. The distant copies of you are as real as you are in the level 1 picture, but no signal from them can ever reach us, and no signal from us can ever reach them. They are epistemically inaccessible forever. Whether this makes them real in a scientifically meaningful sense, or merely in a mathematical sense, is the first instance of the broader philosophical question that the multiverse raises. The second version of the multiverse is the one that most physicists who work on inflation think about when they hear the word. It arises from a specific but extremely well-motivated extension of the basic inflationary framework, and it is called the eternal inflation multiverse, or the level 2 multiverse in Tegmark's taxonomy. The basic idea of inflation, that the very early universe underwent a period of exponential expansion driven by the energy of a scalar field called the inflaton, was developed in the early 1980s by Alan Guth, Andre Linde, Paul Steinhardt, and others, and it solves several problems with the standard Big Bang model that were difficult to address otherwise: the horizon problem, the flatness problem, the absence of magnetic monopoles. Inflation is extraordinarily successful and is supported by the CMB data in ways that have become increasingly precise with each new generation of experiments. But inflation, if it works at all, almost certainly works in a way that produces a multiverse. The key insight was developed primarily by Andre Linde, who realized in the early 1980s that in the most natural inflationary models, inflation never completely stops everywhere at once. The inflaton field has quantum fluctuations, random variations in its value from point to point, built in by the uncertainty principle, and these fluctuations mean that in some regions of space, the inflaton continues to drive inflation even as it ends in other regions. In the regions where inflation continues, the exponential expansion creates new space faster than inflation can end in the old space. The result, as Linde worked out, is eternal inflation, a process in which inflation continues forever in some regions, producing an ever-growing volume of inflating space, punctuated by bubbles where inflation has ended and which evolve into regions with specific values of the physical constants determined by how the inflaton settled into its final state. Each bubble is in effect a universe. Our universe is one bubble. There are infinitely many other bubbles, each with a different history, each with a different final state of the inflaton, and therefore potentially different physical constants, different vacuum energy, different particle masses, different laws of physics. The other bubbles are separated from our bubble by regions of still inflating space. They cannot communicate with us. The inflating space between bubbles expands so fast that no signal can cross it. The other bubbles are physically real, in the sense that the same physics that describes our bubble describes them, but they are permanently inaccessible. The eternal inflation multiverse is the version that most cosmologists find hardest to avoid if they accept inflation at all. Linda has argued that eternal inflation is not a consequence of some specific model of inflation, but of the broad class of models that fit the data, that essentially any inflaton potential that produces inflation of the right kind also produces eternal inflation. Getting rid of the multiverse in this picture requires either finding a model of inflation that does not produce eternal inflation, which is difficult and constrained by the CMB data, or giving up inflation entirely, which faces its own severe problems, since inflation explains observational facts that are otherwise very hard to account for. The third version of the multiverse is the one that physicists who work on string theory think about most carefully, and it is called the string theory landscape. String theory, the theoretical framework that attempts to unify quantum mechanics and general relativity by replacing the point particles of the standard model with tiny vibrating strings, predicts the existence of extra spatial dimensions beyond the three we experience. The geometry of these extra dimensions, how they are curled up, what shape they take, what fluxes thread through them, determines the effective physical constants of the four-dimensional universe we observe. Different geometries of the extra dimensions produce different effective laws of physics in 4 dimensions, and the number of possible geometries, the number of possible ways the extra dimensions can be configured, is, according to current estimates, something like 10 to the 500. This is the string theory landscape, an enormous space of possible universes, each with different laws of physics, each corresponding to a different solution of the string theory equations. The string landscape by itself is just mathematics, a large but finite set of possible universes, each described by a specific set of equations. What turns it into a physical multiverse is the combination with eternal inflation. In eternal inflation, as different bubbles nucleate in the eternally inflating space, each bubble can settle into a different region of the string landscape, a different configuration of the extra dimensions, a different set of effective physical constants. The eternally inflating background samples the landscape, producing a multiverse in which every point in the landscape is realized somewhere, in some bubble. The string theory landscape and eternal inflation together produce what is often simply called the string multiverse, or the landscape multiverse, an ensemble of bubbles, each with a different corner of the 10 to the 500 dimensional landscape of possible string configurations, each with different effective laws of physics. The fourth version of the multiverse is completely different in character from the others, arising not from cosmology or string theory, but from the foundations of quantum mechanics. It is the many worlds interpretation of quantum mechanics, proposed by Hugh Everett in his 1957 PhD thesis at Princeton, and developed and championed by Bryce DeWitt, David Deutsch, and others in the decades since. In the many worlds interpretation, the wave function of the universe never collapses. It always evolves according to the Schrödinger equation, deterministically, continuously, without any special event called measurement that causes collapse. When a quantum system interacts with a measuring device, the combined wave function of the system and device evolves into a superposition of all possible outcomes, not into one specific outcome selected by some mysterious process of collapse, but into all of them simultaneously in different branches of the wave function. Each branch is equally real. Each branch contains a version of the experimenter who sees a specific outcome. From the perspective of any particular branch, the measurement had a definite result. From the perspective of the full wave function, all results occurred in different branches that are now decohered from each other, unable to interfere, and which will never again communicate. Every quantum event that has ever occurred, every radioactive decay, every photon absorption, every neural firing in every brain, has branched the wave function into multiple components, each containing a different history. The number of branches is incomprehensibly large, and each branch in the many worlds interpretation is as real as this one. The multiverse of many worlds is not a collection of spatially separated bubbles, but a collection of quantum branches of a single universal wave function, each branch containing a different version of history, each branch equally real, all of them existing simultaneously in Hilbert space. The many worlds interpretation was initially regarded as an extravagant solution to a problem that had simpler solutions, and it was largely ignored for decades. In recent years, it has gained significant support, particularly among physicists who work on quantum computation and quantum information, and who find the Copenhagen interpretation's reliance on a special process of measurement philosophically unsatisfying. David Deutsch, who invented the concept of the quantum computer, has argued that the many worlds interpretation is the only interpretation of quantum mechanics that takes the mathematics seriously, that treats the wave function as a real physical object rather than a bookkeeping device, and that the existence of parallel universes is a direct consequence of this mathematical realism. The quantum computer, in Deutsch's view, works because computation is distributed across parallel quantum branches. The quantum speedup comes from exploiting the computational resources of a vast multiverse of parallel quantum universes that all contribute to the computation simultaneously. 4 versions of the multiverse, arising from 4 completely different theoretical frameworks. The Level 1 multiverse, from the size of the universe and the uniformity of physical law. The Level 2 multiverse, from eternal inflation and the long-term behavior of inflaton fields. The string landscape multiverse, from the enormous number of solutions of string theory combined with eternal inflation. The many worlds multiverse, from the unitary evolution of the quantum wave function. All 4 pointing in the same direction. Our universe is one of many, the others are real, and we cannot observe them directly. The convergence is striking. It is not the result of a conspiracy among physicists, nor of a fashion in theoretical physics, nor of any single dramatic argument that everyone found compelling. It is the result of each of these frameworks following its own internal logic to a conclusion that was not desired, not anticipated, and that many of the physicists involved have found personally uncomfortable. Andre Linde did not set out to prove that there were infinitely many universes. He was trying to fix a problem with the original inflation model, and the fix led to eternal inflation, and eternal inflation led to the multiverse. The string theorists who computed the landscape of 10 to the 500 possible string configurations were not trying to produce a multiverse. They were trying to find the unique string theory solution that described our universe, and they found instead that there were an unimaginable number of solutions, which was deeply unwelcome to many of them. Hugh Everett did not embrace the many worlds interpretation because he wanted to believe in parallel universes. He embraced it because it was the mathematically consistent consequence of taking the Schrödinger equation seriously without adding an extra unexplained collapse postulate. The multiverse was not sought. It was found, again and again, by different people following different threads of reasoning, all arriving at the same embarrassing destination. The person who has thought most carefully and most publicly about the implications of the multiverse for physics, both its promise and its dangers, is Max Tegmark, a Swedish-American cosmologist at MIT who has spent his career developing and promoting what he calls the mathematical universe hypothesis, the most extreme version of the multiverse idea. Tegmark's argument goes beyond the 4 levels of multiverse described above to what he calls the level 4 multiverse, the claim that all mathematical structures that are self-consistent exist as physical realities, not just the universes produced by different inflaton potentials, not just the different branches of the quantum wave function, not just the different configurations of string theory extra dimensions, but all possible mathematical structures, of any kind, inhabit a physical reality somewhere. Our universe is described by a specific mathematical structure, the equations of the Standard Model coupled to general relativity with specific values of the constants, and we find ourselves in this structure rather than any other because it is the one that contains conscious observers like us, capable of discovering that they exist in a mathematical structure. The mathematical universe hypothesis is the most radical form of the anthropic reasoning that pervades multiverse discussions, and it is also the most difficult to test, since it makes no specific predictions about anything beyond the claim that mathematical consistency is necessary and sufficient for physical existence. Tegmark is unusual among physicists in his willingness to follow the logic of the multiverse to its most extreme conclusions, and to state those conclusions clearly and publicly, without the hedging that most of his colleagues consider appropriate. He has written a popular book, Our Mathematical Universe, making the case for the multiverse and the mathematical universe hypothesis with unusual clarity and commitment. His colleagues have responded with a mixture of admiration for his intellectual courage and concern about his intellectual caution, or lack of it. The most common criticism is that Tegmark's framework, by proposing that everything that is mathematically possible is physically real, has rendered itself completely unfalsifiable. If every possible universe exists, then no observation can be surprising. Every observation is guaranteed to be consistent with some universe in the ensemble. The theory predicts everything, which means it predicts nothing, which means it is not science. This criticism, the falsifiability objection, is the most important and most sustained objection to the multiverse in all its forms, and it deserves to be taken seriously because it goes to the heart of what science is. Science, in the traditional view most associated with Karl Popper, advances by making predictions and testing them. A scientific theory must make predictions that could, in principle, be shown to be wrong. If the theory predicts X and the experiment finds not X, the theory is falsified. This is what distinguishes science from metaphysics, from theology, from pure philosophy, the willingness to put specific claims about the world up against specific observations and be bound by the outcome. Popper himself was explicit. The hallmark of a scientific theory is not that it is true, but that it is falsifiable. An unfalsifiable theory, however beautiful, however internally consistent, however well motivated by the physics that led to it, is not science in the relevant sense. The multiverse, in its dominant forms, appears to be unfalsifiable. The other universes in the Level 2 multiverse are separated from ours by eternally inflating space that can never be crossed. The other branches of the quantum wave function are decohered from ours and can never be observed. The other configurations of the string landscape are in other bubbles that can never communicate with our bubble. No experiment we can perform can distinguish a universe in which these other realities exist from a universe in which they do not. The multiverse is not a prediction in the sense that it predicts some specific observable feature of our universe that we can look for. It is more like a framework, a context within which other predictions can be made but which itself stands outside the reach of any experiment. The defenders of the multiverse have several responses to the falsifiability objection, and some of them are more convincing than others. The first response is to argue that the multiverse is not itself directly testable, but that the theories that lead to it, inflation, string theory, quantum mechanics, are testable, and that the multiverse is simply a consequence of those theories. We do not directly test the quarks inside the proton, but we accept them because the theory that predicts them is supported by overwhelming experimental evidence. Similarly, we may not directly test the other universes produced by eternal inflation, but we can test eternal inflation indirectly through its predictions for the CMB, and if those predictions are confirmed, we should accept the multiverse as a consequence of the confirmed theory. This argument has some force, but it glosses over an important distinction. Accepting the evidence for inflation does not commit you to accepting eternal inflation, and accepting eternal inflation does not commit you to accepting the full ensemble of bubble universes as physically real, rather than merely possible. The inference from the evidence for inflation to the reality of the multiverse involves several steps, each of which can be questioned. The second response is to point out that the multiverse does make some predictions, not about the other universes directly, but about the statistical distribution of properties within our universe, given that we are a randomly selected observer in the ensemble. This is the anthropic approach. Given that we exist, and given that our existence requires certain physical conditions, what can we predict about the specific values of the physical constants we observe? The most famous application of this reasoning was Weinberg's 1987 prediction of the cosmological constant, made before the observational discovery of dark energy. Weinberg argued that if the cosmological constant varies across the multiverse, and if observers can only exist in universes where the cosmological constant is small enough to allow structure formation, then we should expect to find ourselves in a universe where the cosmological constant is close to the maximum value consistent with our existence. He predicted that the cosmological constant should be small but non-zero, and within a few orders of magnitude of the observational bound. The 1998 discovery of the accelerating universe, with a cosmological constant close to Weinberg's predicted range, is cited by multiverse proponents as a successful prediction. The third response is to question the Popperian framework itself, to argue that falsifiability, while a useful heuristic, is not the only criterion for scientific acceptability, and that the multiverse, while not directly testable, is nonetheless the best explanation of certain observed features of the universe. The argument is that the fine-tuning of the physical constants, the fact that the constants take values that permit the existence of life, in a range that appears to be a tiny fraction of the space of all possible values, demands an explanation. The multiverse, with anthropic selection, provides one. The constants are what they are because we could not exist to observe them if they were otherwise, and the other possible values are realized in other universes that we cannot observe. The alternative explanations are either that the constants are fixed by some deeper theory yet to be discovered, which is possible but speculative and currently unsupported, or that they are simply coincidences, which seems profoundly unsatisfying given the extraordinary precision of the fine-tuning. The multiverse, in this view, is not less scientific than its alternatives. It is more scientific because it actually explains something. the fine-tuning, that its alternatives leave unexplained. The critics do not accept this argument, and their response goes to the heart of what explanation means in science. George Ellis, a distinguished cosmologist who has been one of the most persistent and most thoughtful critics of the multiverse, has argued that explaining fine-tuning by appeal to an unobservable ensemble of universes is not scientific explanation in any meaningful sense. It does not predict anything, it does not constrain anything. It simply relocates the mystery from the question of why the constants are what they are, to the question of why the ensemble has the properties it has, and the second question is at least as hard as the first, and typically harder. Richard Dawid, a philosopher of physics at Stockholm University who has thought carefully about the epistemology of the multiverse, has argued that the multiverse requires a new framework for scientific assessment, what he calls non-empirical theory confirmation, in which theories can be evaluated on the basis of their explanatory power and their theoretical virtues even when direct empirical testing is impossible. Others find this proposal troubling, worrying that it opens the door to any sufficiently beautiful and internally consistent idea claiming scientific status, regardless of its testability. The argument has become more intense as the string theory landscape has developed, and as it has become clear that string theory, despite decades of effort by some of the most talented theorists in the world, has not produced a unique prediction for the standard model, has not identified the specific configuration of extra dimensions that produces the physics we observe, and ruled out all others. Instead, the landscape of 10 to the 500 possible configurations has suggested to many string theorists that the reason we observe the specific standard model we observe is anthropic. We observe it because it supports life, and most of the other configurations in the landscape do not. This has been deeply controversial within the string theory community itself. Leonard Susskind, one of the founders of string theory and one of its most distinguished practitioners, embraced the landscape and the anthropic selection in a 2003 paper that generated enormous controversy and a book called The Cosmic Landscape, in which he argued that the multiverse was the only sensible response to the landscape. Other string theorists, including David Gross, one of the Nobel laureates who developed quantum chromodynamics, have been strongly opposed. Gross has argued that the anthropic principle is a cop-out, a counsel of despair, a claim that the laws of physics are what they are for no deeper reason than that they support our existence, and that accepting this is abandoning the scientific program. The argument between Susskind and Gross is not just a disagreement about physics. It is a disagreement about the nature of scientific explanation and about what physics is for. The traditional dream of fundamental physics, from Newton to Einstein to the current generation, has been the dream of a theory that uniquely determines the laws of nature from some deeper principle, a theory in which the constants of nature are not free parameters but necessary consequences of the mathematical structure. The multiverse, in the string landscape version, abandons this dream. It says the constants are not determined by any deeper principle. They are random, in the sense that their values are determined by which region of the landscape was randomly selected by the nucleation of our bubble in the eternally inflating space, and we observe the values we observe for no deeper reason than that they support our existence. If this is true, the dream of a unique theory of everything, a theory that explains why the electron mass is what it is and why the cosmological constant has the value it has, is not just unfulfilled, but unfulfillable. The multiverse is the death of the traditional scientific dream, or it is the realization that the dream was misconceived from the beginning. There are physicists who have taken a middle position on the multiverse, accepting that the theoretical arguments for it are serious, and that the dismissal of it as mere speculation is too quick, while also insisting that the case is not yet strong enough to abandon the search for a more conventional explanation of the fine-tuning. Paul Steinhardt, who was one of the original developers of inflation in the early 1980s, and who has since become one of the most prominent critics of eternal inflation and the multiverse, has argued that the fine-tuning of the cosmological constant and other constants is not actually explained by the multiverse and anthropic selection, that the anthropic reasoning can always be applied to produce the observation we make, regardless of what the underlying probability distribution is, and therefore does not actually constrain anything. Steinhardt has developed alternative models of the very early universe, bouncing cosmologies, cyclic models, that attempt to explain the properties of the observable universe without invoking eternal inflation or a multiverse. His models have their own serious problems, and they have not achieved the success of inflation in explaining the CMB data, but they represent the ongoing search for an alternative. The question of whether the universe is fine-tuned at all, whether the physical constants really do occupy a tiny sliver of the space of possible values consistent with the existence of life, is also contested. The fine-tuning argument relies on a specific notion of what the space of possible values looks like, and there are physicists who argue that this notion is ill-defined or that the argument is much less compelling than it appears. Victor Stenger spent years arguing that the fine-tuning was grossly exaggerated, that a much wider range of physical constants would be consistent with some form of complexity and potentially some form of life, and that the claim that we are in a vanishingly small corner of the space of possible life-permitting universes is based on holding all other constants fixed while varying one, which does not accurately characterize the full space of possibilities. Other physicists have taken Stenger's argument seriously while concluding that the fine-tuning, while not as dramatic as sometimes presented, is nonetheless real and significant and demands explanation. The debate about the degree of fine-tuning is ongoing. Lee Smolin, one of the founders of loop quantum gravity and one of the most philosophically sophisticated physicists currently working, has proposed a specific alternative to the anthropic multiverse that attempts to preserve the scientific ideal of testability while still invoking a kind of multiverse. Smolin's proposal is called cosmological natural selection, and it draws an explicit analogy with biological natural selection. In his model, black holes give birth to new universes. When a black hole forms, it produces a new universe in its interior with slightly different physical constants, analogous to the slight mutations that occur in biological reproduction. Universes that maximize the production of black holes, which correlates with having the right conditions for star formation and stellar evolution, produce more offspring, and therefore dominate the ensemble. Our universe has the physical constants it has not, because they are randomly selected from an ensemble, but because they have been selected by a process analogous to natural selection, optimizing for black hole production. This proposal makes a specific, testable prediction. The physical constants of our universe should be near a local maximum for black hole production. Small changes in the constants should reduce black hole production. Smolin has argued that the constants do appear to be near such a local maximum, and he has spent years trying to develop and test the prediction more precisely. Smolin's proposal has been criticized on several grounds. The mechanism by which a new universe forms in a black hole interior, with modified constants, is highly speculative and not derived from any confirmed physics. The prediction that the constants are at a local maximum for black hole production is difficult to test precisely, and some calculations suggest that the prediction is not in fact satisfied. But the proposal is scientifically admirable precisely because it makes specific, potentially falsifiable predictions, unlike the anthropic multiverse, which Smolin has criticized at length in his book The Trouble with Physics. Whether or not Smolin's specific proposal is correct, it illustrates the scientific ideal that the multiverse advocates are accused of abandoning, the ideal of a theory that explains the properties of our universe by deriving them from a specific, testable mechanism. The argument about the multiverse has taken on a social dimension as well as a scientific one, because it involves disagreements not just about physics but about careers, funding, institutional power, and the direction of the field. String theory, with its landscape of 10 to the 500 solutions, has dominated a significant fraction of theoretical particle physics for 40 years, consuming an enormous amount of intellectual talent and research funding. The LHC's failure to find supersymmetric particles, the particles that string theory requires at low energies in its most natural formulations, and that were expected to show up at LHC energies in the version of string theory that many practitioners were committed to, has been a significant blow to the program, though not a death blow, since the theory is flexible enough to accommodate the null result by moving the superpartners to higher masses. The multiverse and the anthropic principle, in this context, serve partly as an explanation for why the constants of nature, including the masses of the superpartners, might not be at the values that the most natural theories predict. Some critics have accused the multiverse of serving as a get-out-of-jail-free card, a way of explaining away the failure of specific theoretical predictions by appeal to an untestable ensemble. This is perhaps uncharitable, but it is not entirely unfair. The physicist Sabine Hossenfelder, who has written the book Lost in Math, and who has been one of the most trenchant critics of the direction of theoretical physics in recent decades, has argued that the field has become too enamored of mathematical beauty and theoretical elegance, and not disciplined enough by experimental constraints. The multiverse, in her view, is the reductio ad absurdum of this tendency, a theory that is beautiful and mathematically sophisticated and completely untestable, that explains everything by explaining nothing, that has absorbed the attention of the best theoretical minds in physics for decades without producing a single prediction that has been tested and confirmed. She is not alone in this view. Many experimental physicists, who spend their careers designing and running experiments and who are deeply suspicious of theoretical claims that cannot be tested, share her concern, but there are also physicists of the highest distinction who find the multiverse not just unavoidable but genuinely illuminating. Steven Weinberg, who won the Nobel Prize for the unification of the electromagnetic and weak forces, and who is one of the most distinguished living physicists, has been one of the strongest supporters of the anthropic principle and the multiverse since his 1987 paper on the cosmological constant. Weinberg has argued that the success of his anthropic prediction, the 1998 discovery of the cosmological constant at roughly the value he predicted, is evidence that the multiverse is real and that the fine-tuning of the physical constants is a genuine fact about the universe that demands an explanation, and that the anthropic multiverse is the only explanation currently on offer. He has written about the cultural resistance to the multiverse, the discomfort that many physicists feel at the idea that the constants of nature are not uniquely determined, that our universe is not special, that the search for a unique theory of everything is misguided, and has argued that this cultural resistance is not a scientific argument. Alan Guth, who invented inflation and who has spent decades developing the theory and its cosmological implications, is similarly persuaded that eternal inflation and the multiverse are almost certainly correct, that they follow so naturally from the physics of inflation that avoiding them requires more assumptions than accepting them. Guth has argued that the multiverse is the most natural cosmological framework available, that it explains the fine-tuning of the cosmological constant and potentially other constants through anthropic selection, and that the inability to directly test it is a feature shared by many successful scientific theories. We cannot directly test the interior of black holes or the physics of the Big Bang either, but we accept the theories that describe these things because they are consistent with everything we can test, and because they explain things that otherwise would be inexplicable. Andre Linde, who developed the eternal inflation picture that is the cosmological backbone of the multiverse, has thought about the implications of the multiverse more deeply and for longer than almost anyone else, and his perspective is nuanced and sometimes surprising. Linde has argued that the multiverse is not an embarrassment for physics but a liberation, that it frees cosmology from the need to explain why our specific set of physical constants was selected, because in the multiverse all sets are selected, and we observe ours because it supports our existence. He has also argued more recently that some of the properties of the multiverse may be accessible to observation, specifically through the search for remnants of collisions between different bubble universes in the CMB, the so-called bubble collision signatures, which would appear as specific patterns in the CMB temperature fluctuations. These signatures have been searched for and not found, which constrains but does not rule out the multiverse. Future CMB experiments may push the constraints further. The bubble collision search is one of the most interesting developments in the observational study of the multiverse because it represents a genuine attempt to make the multiverse testable, to find a specific observational signature that would distinguish a universe in a multiverse from a universe that is the only universe. The specific prediction is that if our universe bubble collided with another bubble during the period of reheating after inflation ended, the collision would have left a specific imprint on the CMB, a roughly circular patch of sky where the temperature fluctuations are different from the surrounding region, with a specific profile that depends on the parameters of the collision. Several groups have searched for such signatures in the WMAP and Planck CMB data. The search is difficult because the expected signal is small and must be distinguished from random fluctuations and from the systematic effects of the instruments. No convincing signature has been found. The null result is consistent with no collision having occurred, or with the collision signature being too small to detect with current instruments. Future experiments with higher sensitivity may find something, or may push the constraints to the point where collisions of the expected type can be definitively ruled out over a significant range of parameters. The question of what it would mean to find the bubble collision signature, or more dramatically, to fail definitively to find it, is itself interesting and contested. If the signature were found, it would be extraordinary evidence for the multiverse, a specific, predicted observational consequence of a specific multiverse model, confirmed by observation. It would not prove that the multiverse is real in any absolute sense, since alternative explanations might be possible, but it would represent exactly the kind of indirect observational evidence for unobservable entities that physics regularly accepts. If the search definitively rules out bubble collisions of the expected type and scale, it constrains specific multiverse models, the ones that predict collisions of detectably large amplitude. It does not rule out all multiverse models, since the collision amplitude depends on specific parameters that can be adjusted. The multiverse, once again, is flexible enough to accommodate a null result, which is both a feature and a bug. There is one more dimension of the multiverse discussion that deserves attention, because it connects the physics to the deepest questions about meaning and value, and the human situation in the universe. If the multiverse is real, if our universe is one of an infinite number, each with different laws of physics, each containing different histories, each producing in the ones that can produce anything different forms of complexity and consciousness, then what does this mean for how we think about ourselves and our place in the cosmos? The Copernican revolution removed the Earth from the center of the solar system. The galactic revolution removed the solar system from the center of the Milky Way. The cosmological revolution revealed that the Milky Way was one of hundreds of billions of galaxies in the observable universe, with no privileged location. Each demotion was initially disturbing and eventually absorbed, incorporated into a new picture of the human situation that found dignity and significance not in centrality, but in consciousness, in the fact that we are the part of the cosmos capable of understanding the cosmos, however marginal our physical location. The multiverse is a demotion of a different and more radical kind. It demotes not our location, but our laws, not our position in space, but our physics. It says that the specific laws of physics that we have been trying to understand for 400 years, the laws that we have spent so much effort deriving and testing and refining, that we have built the most sophisticated instruments in human history to probe, that some of us have given our lives to understand, are not universal, not fundamental, not necessary. They are local, they are accidents. They are the specific corner of the landscape that was randomly selected when our bubble nucleated in the eternally inflating space, and they could have been different, and in the rest of the multiverse they are different. And there is no deeper reason they are what they are beyond the anthropic fact that they support our existence. This is not just an intellectual blow, it is an existential one. The scientific program of understanding the laws of nature, which has been one of the great collective intellectual enterprises of human civilization for several centuries, is in the multiverse picture not the project of understanding the fundamental structure of reality, but the project of mapping a local accident. The laws we discover are not the laws of the universe. They are the laws of our universe, which is one of an infinite number, most of them with completely different laws that we will never know. The mathematics that we find so beautiful, that we take as evidence that we are uncovering deep truths about the structure of reality. It is the mathematics of one particular realization, of one particular region, of one particular landscape. The sense that the laws of physics are leading us somewhere meaningful, toward a unified theory that explains everything, is in the multiverse picture an illusion. There is no everything. There is only here. Some physicists have found this genuinely liberating. It frees them from the perhaps grandiose expectation that human minds, evolved on a small planet for the purpose of surviving on that planet, are capable of grasping the ultimate structure of reality. Perhaps we are not. Perhaps the ultimate structure of reality is the full multiverse, and the part of it we can understand is the part we live in, and that is enough. The local map is still a map. The local physics is still beautiful. The fact that it is not universal does not make it less true in the only context we have access to. Others have found it deeply depressing, and not just aesthetically. The physicist Paul Davies has argued that the anthropic multiverse is not just scientifically unsatisfying, but that it represents a retreat from the Enlightenment ideal of rational explanation. The ideal that the world is intelligible, that it has an explanation, that the laws of nature are what they are for a reason that we can discover. The multiverse says there is no reason. The laws are what they are because they are what they are in this bubble, and the fact that they support our existence explains why we observe them but does not explain why they exist. This is not explanation, it is the abandonment of explanation. Whether you find the multiverse liberating or depressing, illuminating or empty, depends in part on what you expected from physics in the first place. If you expected physics to explain why the universe is the way it is, to derive the laws of nature from some deeper principle that leaves no room for accident or contingency, then the multiverse is a disappointment. If you expected physics to describe the universe as accurately as possible, without any commitment to a specific form of explanation, then the multiverse may be the most accurate description available. The argument is not settled. It may never be settled. The other universes may remain forever inaccessible, their existence inferred but never confirmed, their properties speculated about but never measured. The multiverse may remain, permanently, the most important and most contested idea in cosmology, the idea that is taken seriously by the most serious people and dismissed by the most serious critics, the idea whose evidence is compelling and whose testability is absent, the idea that answers the deepest questions about fine-tuning and initial conditions by pointing to a reality we can never observe, or the argument may be settled in ways we cannot currently anticipate. The bubble collision signature might be found in future CMB data. The string landscape might be mapped precisely enough to make specific predictions about the low-energy physics that can be tested at accelerators. The neutrino sector might reveal CP violation at a level that confirms leptogenesis and constrains the early universe in ways that bear on inflation and eternal inflation. The quantum foundations of the many worlds interpretation might be tested in quantum information experiments in ways that distinguish it from alternative interpretations. Physics has a habit of settling questions that once seemed permanently beyond reach, and the history of science is full of examples of ideas that seemed like pure metaphysics and turned out to be testable, and ideas that seemed like solid science and turned out to be empty. The multiverse could go either way. What is clear, and what is worth holding on to even in the midst of the debate, is that the question the multiverse is trying to answer is real and important. The physical constants are what they are. Some of them appear to be extraordinarily well suited to the existence of life. The question of why they have these values and not others is a genuine scientific question that demands an answer. The multiverse is one answer. It may be the right answer. It may be the wrong answer. But the question is not going away, and it deserves the attention that the most serious physicists have been giving it, and the skepticism that the most serious critics have been bringing to it, and the patience to wait for the evidence, whatever form it eventually takes, to tell us something definitive. You are here, in this universe, with these laws of physics, asking this question. Whether there are infinitely many versions of you in infinitely many other universes asking the same question, or whether you are the only version that exists in the only universe there is, asking a question that has no answer beyond the brute contingency of the initial conditions, is the most important question in cosmology and one of the most important questions in all of science, and it is open. It is genuinely, profoundly, stubbornly open. The universe has been generous in answering questions. It gave us the CMB and the Higgs boson and gravitational waves and the accelerating expansion and the neutrino oscillation. It has allowed us to peer back to the first moments of the Big Bang and to the edges of the observable universe. It has revealed the structure of matter at the smallest scales we can probe, and the structure of space-time at the largest scales we can observe. But on the question of whether it is the only universe, or one of many, it has not yet spoken. The answer is there, in the physics of eternal inflation, in the solutions of string theory, in the foundations of quantum mechanics, in the distribution of physical constants across whatever ensemble of universes actually exists. The answer is there. We have not yet found the way to hear it. Paul Dirac, sitting with his equation in 1928, found an extra set of solutions and followed them to antimatter. The physicists of the 1960s and 1970s, sitting with the equations of inflation and quantum field theory, found eternal inflation and followed it to the multiverse. Whether the multiverse is real in the way antimatter is real, confirmed, measured, used, incorporated into the ordinary furniture of physics, or whether it is a beautiful but ultimately empty mathematical construct, a shadow cast by our equations but not by reality, is the question that the next generation of physicists will spend their careers trying to answer. The work is not finished. The universe is not done speaking. And the question of whether this universe is all there is, or the smallest imaginable fraction of everything there is, remains, for now, the deepest open question that human thought has ever produced.